All right, pre-calc students, in this video we're going to go through the same example we did in class, but this is finding all the zeros of a polynomial function and writing that polynomial function in this linear factorization. So, according to the fundamental theorem of algebra, which is in your notes prior to this example, a polynomial function of n degree has n complex zeros, real and non-real, and some of these zeros might be repeated. The linear factorization theorem will use this to turn our zeros into factors, and then connecting all those things, if x equals k, k being some constant number, if k is a solution or root of the equation, f of x equals 0, then that number is a zero of the function, so zero of the polynomial. And if that's the case, then x minus k would be a factor. So if k is a 0, or like a number 3 is a 0, then x minus 3 would be the factor. If 10 is a 0, then x minus 10 is the factor. If negative 8 is a 0, then x plus 8 would be the polynomial. There's a linear factor that goes with that. So if we're going to find all the zeros of a polynomial, we first have to know how many we're looking for. And in this case, because it's x to the 5th power, there's going to be 5 complex zeros that we have to go ahead and find. Okay, 5 complex zeros. And that includes real, imaginary, and any repeats that might exist. So my first step for finding the zeros of a polynomial would be to graph this function. Okay, because if I graph the function, the x-intercepts will be the real zeros of that function. So you see here on my graphing calculator, I've got the function typed in. When I graph the function, I notice a couple things about it. I'm going to drag it over here so I can draw it. Oops, don't want that. So as I look at the function, I notice that my polynomial graph crosses the x-axis in a couple of places. So it crosses right here at x equals 2. And then I notice that over here at -1, it's tangent to the x-axis. So what this means is that 2 is probably going to be a 0 of this function. And then over here, -1 probably is also going to be a 0. And if you remember from Algebra 2 and the things that we did, if my graph is tangent to the x-axis, it means that this is probably a 0 more than once. It's probably a repeat. Okay, so I'm just going to make a little note of that -1 is probably going to be a repeat 0 for us. Okay. Now, once I graph it, and I think I might have found some zeros, the other thing I think to myself is, well, I got 1, 2, maybe a third 0. But remember, I had to find 5 total. So that means that the other 2, again, assuming that this is a repeat, the other 2 are probably going to be imaginary in nature, meaning that only real zeros show up on a graph as x-intercepts. Imaginary zeros won't. So if I see 3, I think, that means 2 got to be imaginary. Now to find those imaginary zeros and prove that these are zeros, what I'm going to do is I'm going to plug in these numbers, 2 and -1, using synthetic substitution. So again, if this, remembering this from Algebra 2, I'm going to write out the coefficients of my polynomial. 1, -4, 4, 10, -13, and -14. Okay? And then I draw that half rectangle. Okay, this is how this works, synthetic substitution. Then I'm going to take 2. If 2 is a 0, I'm going to plug in 2. And the way that this process works, if you remember from Algebra 2, I drop down the first number, 1. I multiply the number out here, the 0, times that number, so 2 times 1 is 2. And then I add -4 plus 2, so I get -2. And then I repeat the process. Multiply, 2 times -2 is -4. Add, I get 0. Multiply, 0. Add, 10. Multiply, 20. Add 7, multiply 14, add 0, and that's the key. If I get 0 at the end, that means I have a 0 for a remainder. That means that the number that I plugged in is a 0 of this function. So synthetic substitution, synthetic means fake. If I wanted to take 2 and see if it was a 0 or not, I could use direct substitution, meaning plug in 2 here, and here, and here, and here, and seeing what I get. Well, this is just a faster way of doing that same thing. So when I plug in 2, I get 0. That's great. That means that 2 is a 0 of that function. Okay. Now I'm going to test -1 next. And when I do that, I can actually continue on with my synthetic substitution with the leftovers. Okay. So because I got 0 at the end, I now have some numbers here that represent a depressed polynomial. So if you remember that this process also matches up with long division of polynomials. I've divided x to the 5th by x minus 2, and now I have x to the 4th and some other stuff. Okay, so I'm going to take -1 and plug it in. Drop the 1, multiply, multiply, add, multiply, add, multiply, add. And I get 0 at the end, which is good. So that means that -1 is also a 0 of this function. So I think that -1's a repeat because my graph was tangent at -1. So I'm going to check that out, and I'm going to plug in -1 again into my newly depressed polynomial. So drop the 1, multiply, add, multiply, add, multiply, add, and one more time I get 0 for a remainder, which is fantastic. That means that -1 is also a 0 a second time. Okay. So at this point, just kind of recap what we got going on. If we're looking for zeros, we've got the 3 of them so far. Okay, it would be -1 and -1, count it twice, and 2. So I got 3 real zeros, and now I need the 2 imaginary or complex zeros to go with it to make a total of 5. Okay. The other thing I want you to think about is we're supposed to write out the linear factorization, which means turning those zeros into factors. So take a look at what that would look like. Okay, the factors I've got, if these are the zeros, that means that x plus 1 is a factor, not just once, but twice, because -1 is a 0 twice. Okay, and then if 2 is a 0, well then x minus 2 must be a factor. Okay, so again, remember that when I'm using synthetic substitution and plugging in 2 and -1 and -1 again, what I'm essentially doing is I'm taking this big polynomial that I started with and dividing it by each of these binomial or linear factors. Okay, and when I do that, when I divide, I'm taking initially I had x to the 5th, and I divided it by x minus 2. Now at this level, this polynomial right here represented is x to the 4th and some other stuff, and then I divided it. So now I'm down to x cubed, and I divided it by x minus or x plus 1. So now at this point, these 3 numbers right here, 1, -4, and 7, they represent the depressed polynomial x squared minus 4x plus 7. Now this is a good thing that we've gotten to this level. We started with x to the 5th, and we worked our way down to x to the 4th, and x cubed, and now x squared. X squared is a quadratic expression. So in order to find the final 2 zeros, what I'm going to do is I am going to use the quadratic formula. Okay. Now, many of you have that as an app on your calculator, which is great. You type it in, A is 1, B is -4, and C is 7. If I had to do the quadratic formula by hand, I would take the opposite of B, plus or minus the square root of B squared, minus 4 times A times C. Okay. All over 2 times A. Cleaning this up, well, 16 minus 28 is going to be -12. So I got 4 plus or minus the square root of -12 all over 2. And then I would simplify my radical. That's going to turn into 2i times the square root of 3. And I might write it this, so I'm going to go 2 root 3 times I. I'll put that on the outside. All over 2. Final step, take these 3 numbers, the 4, the 2, the 2. I'm going to factor out a 2 and divide, and I'm going to simplify and get 2 plus or minus the square root of 3 times I. So this would be 1 because I'm adding, and the second one because I'm subtracting the final 2 zeros of my polynomial function. Okay, so I got 0, I got -1, -1, 2, and then 2 plus root 3 times I, and 2 minus root 3 times I. There's my 5 zeros that make up my answer. Last thing I would do is I would take these imaginary zeros and turn them into factors. So the way I would do that, initially I would do this. I'd have brackets, x minus that complex numbers, x minus in parentheses 2 plus the square root of 3 times I. And then I'd close the brackets. And then I'd have another set where I'd be taking x minus the other one, which is going to be, let me get back here we go, x minus parentheses 2 minus root 3 times I. Close parentheses, close the brackets. And then if I had to work, you could write this, I could distribute the negative sign and write it as in parentheses instead as x minus 2 minus the square root of 3 times I. Okay, that's just distributing the negative sign. Same thing over here. It'd be x minus 2 plus the square root of 3 times I. In any case, I'd have 1, 2, 3, 4, 5 linear factors that make up the linear factorization of my large polynomial. So that's a lot of stuff going on in one problem, but at least you got this to look back on, and we'll do some practice in class.